Ladies and gentlemen, class recording has started. All right. In the last unit that we did, we talked about our introduction to physics. And that introduction to physics starts with mechanics, which is the study of motion. Now, mechanics is a pretty broad area, and there's a lot of things you can do within mechanics. We started with one small section of mechanics called kinematics. You don't have to know that word, but kinematics relates to motion only from a description standpoint. We don't try to explain the motion, we just describe it. So we were talking about an object that was moving with an acceleration of 5 meters per second squared, but we really didn't give any thought to why it was moving with 5 meters per second squared. Or an object is slowing down at a rate of 10 meters per second squared, or whatever it is, without any thought to why that was happening. That's what this unit is about. Force starts answering for us the why question. So, let's start with this. What is a force? If I give you that question on a quiz, most of you can probably come up with an answer for me. It would probably sound something like this. A force is a push or a pull. And that's great. But we're more interested in what forces do. Because remember, we're trying to explain why certain things are happening. So, a more descriptive definition of force would be forces cause acceleration. Acceleration is a term that we introduced last chapter. Right? What is acceleration? A change in velocity, or more generally, a change in the motion of an object, right? And we said that there are 3 things that could be examples of acceleration. And what are those 3 things that are examples of acceleration? Speeding up, slowing down, changing directions. Anytime one or more of those 3 things is happening, we have acceleration. Yes, go.
Says forces cause acceleration.
Yes.
And our outline says forces are the cause.
It's different wording of the same thing.
But one comes with the other.
One is. No.
Just forces cause acceleration, and this would be forces are the cause.
One is active voice, one is passive voice. But they mean the same thing, right? Forces are the cause of acceleration.
Teacher.
Cause acceleration. The same thing.
This is saying acceleration causes acceleration.
Yeah. That would be.
They are the cause of the acceleration.
That's not what I
They're
meant.
the effective.
So, yeah, that would be effective acceleration. So
They are the effective, is what you said?
that's what that's what forces do. They cause things to accelerate.
Oh my
Yes. They are what causes acceleration. Yes. Okay.
I answered my own question.
All right. Okay. Continuing on. Forces are vector quantities, meaning they have to tell us 2 things, right? What do they have to tell us? Magnitude and direction. When we talk about magnitude in this case, we have to talk about the how much. And when that relates to forces, that is the how much are we pushing or pulling. But then the direction is also important because which way we're pushing or pulling definitely will have an effect on what kind of changes occur. If I'm pushing something in the same direction that it's going, that's going to have a different effect than if I push something in the opposite direction that it's going. So we have to know how they were pushing or pulling, but then also which way are we pushing or pulling. One of the things that we will do a lot in this unit is look at pictures and analyze motion based on the forces. We will use arrows to represent forces. And I forgot to leave you guys a line there. I apologize. Okay. So we use arrows to represent those forces. The direction part makes sense with the arrow, but we try, at least generally, to represent the magnitude of that force with the length of the arrow. So if you have a force of 10 acting on an object and a force of 5 acting on that object, two different forces, it will be beneficial to help us look at the effect of those forces if we draw the 10 force about twice as long as the 5 force. Doesn't have to be exact, but if you do it kind of ballpark, it'll help you analyze that situation. Good with that? All right, next. How do forces work? There are a couple ways that we can cause this acceleration, that we can cause an object to change what it's doing. The first way we do this is with something we call the contact force. Contact force are what most of you probably think of when we say forces, right? These are your pushes and your pulls and your hits and your throws and your strings that are attached to things and pull them in opposite directions and, your, what?
You sound like Dr. Seuss.
Yeah, so, yeah. And your cranes that lift things off the ground, etc., etc., etc. But there are also some forces out there that don't actually require physical contact in order for you to change the motion of the object. And we refer to those forces as field forces. Things like gravity, or magnets, or oppositely charged particles. Very good.
What about wind?
Wind is a contact force because it's blowing the air and running air into stuff. You know what I'm saying? Even though it may not look like there's contact there, you gotta have air in order for wind to work, But gravity will work even if there is no air. You know what I'm saying?
What if something is on the ground, you stomp on the ground really hard, and then the thing moves? Would that be contact?
Yeah, definitely. It's from the ground. Yeah, it's like the rebound of the ground. Yeah. Something I want you guys to keep in mind, though. So here are two pictures showing objects that are experiencing forces. Now this is going to be a big red line when I go to draw this picture, but do it, bitches. Please discard. Okay? So the picture on the right, you have this guy, he's diving off a cliff, and we learned in the last chapter that he is experiencing an acceleration around 10 meters per second squared coming from gravity, right? And we talked about the idea that 10 meters per second squared means that the velocity of that object changes by 10 meters per second for every 1 second that goes by. Great. This guy on the left over here is applying a force to this box. Picture on the right, this is a field force, right? Gravity causes his object, or gravity causes his motion to change. But this is a contact force because he's actually pushing the box. But what we find out is that he also can cause an acceleration of 10 meters per second squared, meaning that he's going to cause this box to change in velocity by 10 meters per second for every 1 second that goes by. What I want you to understand out of this is that there is no difference in the effect of a field force versus a contact force. It's not that all contact forces are stronger than field forces or vice versa. You can end up with the same acceleration from a contact force as you do a field force, just a different way of doing it. Okay? So don't think that there's something fundamentally different about them. They're just a different way that they work. Right? They both cause acceleration. They both can cause the same acceleration. It's just a different way of accomplishing it. Okay? Questions? All right. Let's go back and let's talk about how we measure force. Force is measured in a unit that is called newtons. You probably can figure out where it got its name from, but if you can't, just wait till tomorrow and we'll explain it to you. Okay? By definition, 1 Newton is the force that is required to cause an acceleration of 1 meter per second squared on a 1 kilogram object. That's how we define the Newton. We'll explain this a little bit more, so don't, if that makes no sense to you, it's okay. We'll explain a little bit more about what that means. So 1 Newton is the force required to cause an acceleration of 1 meter per second squared on a 1 kilogram object. So let's take this picture. Let's take a look at this hockey puck. And let's say, for argument's sake, that this hockey puck has a mass of 1 kilogram. Hockey pucks don't weigh 1 kilogram or don't have a mass of 1 kilogram, but let's say it does. And this hockey puck is on an air hockey table, so it doesn't have any friction. And this hand applies a force of 1 Newton. Okay? 1 kilogram worth of mass, 1 Newton force. If 1 second goes by, the velocity of this object is going to change. By how much? By 1 meter per second. So if it was at rest, after 1 second, it's going to be going 1 meter per second. Okay? Does that make sense? As far as what a Newton is and how we define it, what kind of acceleration it causes, right? If we bumped this up to say, I don't know, let's say, just to keep it consistent, we'll go with 11 newtons, right? If I bump this up to 11 newtons worth of force, 1 kilogram still, 1 second still, how fast would this object be going? 11 meters per second. Okay? Are we good with that idea that that's how force works? It causes an acceleration, and that acceleration is, it shows up in the change in the velocity. Go ahead, Frank. That would be how quickly are we changing the velocity of that object. Okay? Now, Farah, I could mess around with it a little bit. If I kept this at 11 newtons, okay, but then made this time over here 11 seconds, it would only go from 0 up to 1 then, because you're spreading that force out over a longer time. Does that make sense? All right.
Are we gonna have a formula for like the more complex something?
Yes. I should have written that down for you, Becca. I'm sorry. What we find out, Becca, is that 1 Newton is actually a derived unit that is a combination of a bunch of other units. Okay? 1 Newton is defined as 1 kilogram time meter over second squared, which takes into account the mass of the object that we're moving and what kind of acceleration it causes. This is not exactly at this point real intuitive about where it comes from, but after tomorrow's discussion, we should see a little bit easier where this comes from. But just keep in mind that whenever you see this unit here, it's really a combination of these 3 units. So for purposes of like doing conversions and stuff like that, just keep in mind that Newton is a shorthand way of writing all those units. Good there? All right. Let's finish this off by going here. Okay. Yeah, don't go there. Go back. Okay. So, the back of this page takes into account something that we see as scientists look at the different kinds of interactions that exist out there in the universe. The different kinds of accelerations. All the ways that things can speed up or slow down or change directions. And what we find is that if you take a look at all the kinds of accelerations that occur, there are similarities between them, and that they fit into categories. And we've done this before, right? We take a big list of things and put them into categories because they're similar. We find out that forces are like that as well. there are only certain kinds of forces that exist out there in the universe. And we refer to these as the fundamental forces that exist in the universe. Now, we'll warn you. The stuff I'm about to tell you is a little bit outdated. Your book has not been updated for a while, and since the last time your book was published, there have been changes to how we feel about these different fundamental forces and how we classify them. So, if you go home and your physicist dad is looking at your outline and says, this is wrong, just say, yeah, Dad, I know, we learned that it wasn't quite right in class, but we're going to stay consistent with what we did in the book. Okay, so, yeah. So, just tell him that your teacher told you that it wasn't exactly right, and he's aware of that. Okay?
So you're teaching us the wrong information?
Yeah.
Man, math teachers do that all the time.
What?
How does math ever go
No,
wrong?
like math, they're like, oh, you should do it this way, and then the next part, they're like, oh yeah, you learned it that way, but we're gonna make you do it this way because it's easier for this class, and then they're gonna switch it up the next
Gotcha.
year.
That's not wrong, that's just teaching you a different way to do it.
No,
So,
But they act like the way they isolated.
that's actually how they do everything, though.
They act like the way that
They
you
want
do it is
the
wrong.
new way and they mark it wrong.
that could be. That doesn't mean it's wrong, it's just not the way they wanted you to do it.
Well, then they shouldn't be so picky.
That doesn't mean it's wrong, it's because it's wrong at the test.
I'm sorry.
Okay, so, the first type of force we talk about is an electromagnetic force. Electromagnetic forces we have talked about extensively in this class. Okay? That this is the force that exists between charged particles. First, where do charged particles come from? Atoms, right? They're parts of atoms. And we find that, depending on the combination, they will exert forces on one another. They will cause each other to change their motion. Sometimes they attract, sometimes they repel. This depends on the combination that you have. Okay? This is one kind of force. It's also the only kind of force that we see that can do both. That can be both an attractive force and a repulsive force depending on the situation. Pretty much all of chemistry is based on electromagnetic forces. We talked about chemical bonding. Chemical bonding is an attractive force between two oppositely charged ions. We talked about electricity and how the flow of electricity, current, is based on the repulsion between electrons in one part of the wire and electrons in the other part of the battery. So almost all of chemistry is based on electromagnetic forces. Good there. We okay with that? All right. Next. The strong nuclear force. We've also discussed the strong nuclear force in this class on a couple of occasions. Most recently in the nuclear energy unit. Where does the strong nuclear force come into play? In the nucleus, right? Because, Maddie, what's in the nucleus? A bunch of protons, right? And a bunch of neutrons, too. What do all those protons do to each other? They repel.
I know that.
If there wasn't anything holding them together, would they stay in the nucleus? No. Right? Now, the wording that I have up here on the board is a little bit different than the wording in your outline. Because this morning when I was looking over my stuff before class, I realized that the way it was worded up here on the board wasn't good. So, the strong nuclear force is a force of attraction that acts on protons in the nucleus. It doesn't act on protons and neutrons. Neutrons don't need a force to hold them together. They don't repel or attract anything. Okay? And it's caused by neutrons. And I also realized today that I spelled neutrons wrong. So, once again, don't go home and tell your dad that your science teacher doesn't know how to spell neutrons. Right? So, it could be your mom too, right? I don't want to stereotype, but it could be your mom. Don't go home and tell your mom that I don't know how to spell neutrons either.
Or that you think that matters.
I'm just saying.
Wait, so what do we
There are women scientists out there.
yeah. Aim it for-
But one thing we find out about the strong nuclear force, it is a very strong force, but it doesn't act over a very long or a very big distance. It basically acts within the nucleus, and that's it. Once you get outside of the nucleus, you don't feel the effect of the strong nuclear force. I can't use the strong nuclear force to help pick up this remote control. It doesn't work that way. Okay? You basically don't see the effect of the strong nuclear force in your everyday life, except for the fact that your atoms that make up your body don't spontaneously decay, which would be bad for you. Okay? Yes, Meg?
What's the number 1 under
Attractive force that holds protons together in the nucleus. Okay? And where it says B, where it says the strong nuclear force acts on the nucleus of the atom on protons and neutrons, get rid of the and neutrons part. Okay? Because strong nuclear force doesn't act on neutrons because there's no need for it to act on neutrons.
Are we skipping the examples?
Yeah, the examples you can, I'm going through it because I want to get through all the information. So. All right, next, the weak nuclear force. How about you do this for me, okay? See where it says letter C and there's a blank spot? Write weak nuclear force in there and let's just forget about it, okay? Weak nuclear force is one of those ones that sort of has been assimilated into the other forces as the scientists work on a unification theory, which means they're looking at coming up with a way to really say that all these forces are the same thing, just different versions of the same thing.
Well,
Okay?
yeah.
So let's just move on here. All right, and let's talk about gravity. Definitely, gravity is one we got to talk about. Okay. So first, we know a little bit about gravity, right? What does gravity do? Well, that's one thing that does, but more generally, okay, gravity is an attractive force. It pulls things together. But it is an attractive force that exists between any two masses that exist in the universe. So any two objects that have mass, there is a gravitational force between them. There is a gravitational force between you and the pencil that you are using to fill out your outline. There is you, well,
Everybody
okay.
just dropped it.
You and the writing utensil that you're, okay. There is a gravitational force between you and the outline you are filling in right now. There is a gravitational force between you and the person sitting next to you. Okay? Yes. They are attracted to you. Just like you always do. So, okay. All right. Because any two objects that have mass have gravity between them. However, what we find out is that if we look at the kind of interactions and the amount of force that is required for these different interactions, gravity is a relatively weak force when you compare it to the other forces. Now you might say to yourself, wait a minute, gravity is not a weak force. It keeps me from flying off of the Earth. And if we want something to leave the Earth, we have to strap it to a huge rocket that applies a huge force, right? And it's strong enough for the sun to keep planets in orbit that are like 2 billion miles away. That doesn't sound weak to me. That's true. But gravity, when you compare it to the other forces, is a relatively weak force. Example, the next time you're at a celebration that has balloons in it, right? You take a balloon, you rub it on your hair, assuming you have hair, of course, right? You take it and you stick it to the ceiling. And what happens? Stays there, right? You rubbing that balloon on your hair required, okay, causes a positive or negative charge to develop on that balloon. And it's attracted to that negative or positive charge that is on the ceiling. Is gravity still acting on it? Yeah. But all of the gravity of the Earth is not enough to pull that balloon off of the ceiling that's being held there by some positive and negative charges. Gravity is a relatively weak force when you stack it up against the other forces. But if you get enough mass, it can have significant effects. Okay? Good there? Alright, how much gravity is there? Well, it depends. The greater the mass of the objects, the greater the gravitational force between them. What kind of relationship does that sound like? That's a direct relationship. The amount of gravity that exists between two objects directly depends on the mass of those objects. As the mass gets greater, the amount of gravity gets greater. But that also means that as we sit here in this classroom, you all are feeling gravity, but you are not all feeling the same gravity because you are attracted to the Earth. The Earth has the same mass for all of you, but you're all different masses, meaning that the Earth attracts you differently, different amounts of force. Now, later on in this unit, we'll see that force isn't the only thing that is responsible for the motion of the object. That even though the Earth is pulling on all of you differently, you still feel the same acceleration because of that force. Yes, ma'am?
So, if there was no gravity, would we all be the same height? 'Cause
Not
during
necessarily.
the day, aren't we being pushed down by gravity?
Yeah.
And that's why we're the height we are.
Not necessarily, because that would also depend on how much mass you have and how much positive and negative attraction it all has. So we couldn't necessarily say that, but your height would remain constant throughout the day as opposed to getting smaller as you go throughout the day.
It's shorter, yeah.
But the amount of gravity that exists between two objects also depends on the distance between two objects. That as the distance increases, gravitational force decreases. What kind of relationship does that sound like?
Inverse.
That's an inverse relationship. But when we take measurements about how much force there is versus how much separation there is between those objects, we find that it is not just a straight up inverse relationship. It's something that we call an inverse square relationship, where the amount of force that is acting on the object, represented by this F, is proportional to 1 over the distance squared. So, as I stand here 1 meter away from Nicole, there is a gravitational force between us. If I move back, so now there's 2 meters between us, that gravitational force decreases. But it's not half as much, it's 1/4 as much, because we put a 2 in there, and 2 squared is 4. Okay? Good there? Alright, hold on, we have plenty of time. Okay? So, a couple of things. First, if you look at the calendar, there is a reading assignment from Friday that relates to sections from the book that go over these topics. But then also for tonight, there is some problems from the book dealing with there's introduction to forces and stuff like that. Okay, so take a look at those. Okay. One last thing. This is kind of important, not because it's your homework, but because it relates to you guys over the next couple years. None of you are old enough to vote, but your parents are. So if you make sure that your parents get out and vote tomorrow, because it's important for you guys over the next 3 years not to lose funding for things you like to do and programs that you think are good and stuff like that. Sometimes, depending on if the line is long, some people are just like, oh, this is such a hassle. Please convince them that it's worth just staying there, standing in the line if there's a line, and stuff like that. Okay?
Yeah, we have like 4.
So, real need everybody, proving value. So.
What's